So the main calculation type in chapter 14 is to do calorimetry problems. So for calorimetry, we need to talk about the heat flow from one object to another. So heat is actually energy. It goes from hot to cold. It has a direction, and the symbol that we use for it is Q. The SI unit will be joules, but often we talk about calories, where calorie is the heat to change the temperature of 1 gram of water by 1 degree C, and a calorie is just over 4 joules, 4.186 joules. The calories with a capital C that you see on the back of a candy bar wrapper is actually a kilocalorie, which is 1,000 calories or 4,186 joules. In this country, the unit used for heat when you buy something like a heater, for example, or an air conditioner is British thermal units, BTU, where 1 BTU is just over 1,056 joules. It's the heat that's needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So to change the temperature of an object, we need to add heat to it. And the amount of heat that we need to add to change the temperature depends on what the material is made of. And the material has a specific heat, C, that depends on what it's made out of. And this specific heat is the heat that's needed to change the temperature of 1 kilogram of the material by 1 Kelvin, or equivalently by 1 degree C, since a step of 1 Kelvin is the same as a step of 1 C. So the heat Q that you have to put in is equal to the mass times the specific heat times the temperature change that you want to get. For water, the specific heat is 1 calorie per gram degree C, or 4,186 joules per kilogram Kelvin or kilogram C, which is much higher than for most other materials. So that's why it takes a lot of energy to boil your water on the stove. And if you put your hand in some water, it'll either get cold very quickly or hot very quickly, because the water has a very high specific heat. It won't change compared to your hand. For calorimeters, we also talk about an isolated system and a closed system. In an isolated system, no heat is lost. So for example, in the picture shown there, you have an insulator around the material, and so the heat that's lost by one object just gets transferred to the other, and no heat exchanges into the world. And in a closed system, no mass enters or leaves. So it could be something, for example, like you get a bottle of cold water from the fridge and you leave the lid on. That's a closed system. No mass enters and leaves, but your bottle of water will still warm up, so heat energy is exchanged. So closed and isolated are different to each other. So a calorimeter is just a closed, insulated container of water so that no heat can exchange and no material goes in or out. So it's both closed and isolated. So in general, what we do is we drop in a hot object into some water and we measure the change in temperature as it comes to thermal equilibrium with the water. And from that, we can get the specific heat of the material. Another thing that can happen when you heat something up or cool it down is that it can change its phase. You remember the 3 physical states that we talked about? Liquid, solid, and gas. A phase changes when you go between those different phases. So during a phase change, heat is either absorbed or released due to the breaking or the formation of bonds. And while it's changing its phase from one to another, there's no temperature change involved. So if I melt something, so if I take an ice cube out of the fridge and I melt it, turn it from a solid into a liquid, I'm absorbing heat from the room, or from your glass of liquid. So if you throw an ice cube into your glass of water, the glass of water gets cooler because heat is absorbed from the water to melt the bonds in the ice. And while the ice is changing from a solid to a liquid, its temperature will not change. If I go the other way, that's called freezing, where I go from a liquid to a solid. And what happens then is that heat is released as the bonds are formed. And so your room will actually heat up a little bit. Boiling, you go from a liquid to a gas, and in that case you absorb heat. Condensing, you go from a gas to a liquid, and heat is released. And sublimation is going straight from a solid to a gas, and in that case, heat is absorbed. So whenever you go from a more ordered to a less ordered state, it absorbs heat. Whenever you go from less ordered to more ordered, it releases heat. And the amount of heat that's released is called the latent heat, and the word latent means hidden. Okay, so the latent heat, L, is the amount of heat that causes 1 kilogram of the object to change its phase, so either to melt or to freeze or to boil. So the heat Q that you need is equal to the mass of material that you have times the latent heat of transformation, and again that latent heat will depend on what the material is. So let's look at an example here of where we take some ice from the freezer that's at minus 40 degrees C and we turn it into steam. So what's going to happen is initially, as we take the ice out of the freezer, it's going to warm up until it gets to its melting temperature, which is going to be 0 degrees C. So during that phase, we're in the gray region at the very left side of the graph, it's going to absorb heat, causing a change in temperature. So the heat we're going to use is mc delta T. So it's going to be mass times the specific heat for ice, this should be Ci, times the temperature change. Then once the ice gets to 0 degrees C, it's going to start melting. And while it's melting, it's going to stay at 0 degrees C, but heat is going to be absorbed into the material, and the amount of heat that it's going to absorb is going to be the mass of the material times the latent heat of fusion. So if it goes from solid to liquid or liquid to solid, it's called the latent heat of fusion, LF. That's absorbed to change 1 kilogram of material from a solid to a liquid, or the heat released to go from liquid to solid. Okay, so now once all the ice is melted, then what's going to happen is it's going to be able to warm up again. So now it's going to be turned to complete liquid, and now that water is going to start absorbing heat and warm up. And it's going to warm up till it reaches its boiling point, which is 100 degrees. So during that phase, which is the green stage on that graph, it's going to be absorbing heat, mc delta T, and the amount of heat it will absorb is from 0 degrees to 100 degrees, so a temperature change of 100 Kelvin or 100 degrees C, times the mass times the specific heat of the liquid. All right, so now once I've got it to the boiling point for water, now it's going to start vaporizing. So now it's going to start absorbing heat while its temperature stays at 100 degrees C. So that's the big long pink region. It takes an awful lot of energy to turn water into steam. So while it's in that phase, you have the latent heat of vaporization, LV, is what controls how much heat you need to pump in to change the phase. So the amount of heat is going to just be LV times the mass of water that we have. Once all the water has been turned into steam, excuse me, then we get to the yellow region on the far right, where now all the water is turned into steam, and now the steam, if we put more heat in, will increase in temperature, and then we'll get back into a heat of mc times delta T. So while the temperature is changing, the heat that goes in or out is mc delta T. While it's changing a phase, the temperature stays the same, and the heat is L times the M. And there's no change in temperature during the phase change. So if we want to solve calorimeter problems, we first need to make sure that the problem states that it's an isolated system. So the heat that's lost by one object is going to be the heat gained by the other. Always look and see, are you close to, say, the boiling temperature of water? Does it look like there's going to be a phase change? If there is, then for the heat we have to write mc delta T plus Lm. But if there's no phase change, then the heat is just going to be mc delta T. Then we need to write each side of the equation so that it's positive. So what I mean is make sure that delta T is such that that delta T is going to give you a positive number, and solve for the unknown. So let's do an example. So here I've got 50 grams of copper at 200 degrees C is dropped into a calorimeter containing 150 grams of water at 20 degrees C. And I want to know what's the final temperature of the system. So the water is going to warm up when you drop the hot metal into it, and the copper is going to cool down, and they're going to reach equilibrium at a constant temperature. So the question is, what's the final temperature of the system going to be? So let's write down again what we know. So we know the mass of the copper is 50 grams. And let's put that into kilograms, 0.050 kilograms. The temperature of the copper, the temperature of the copper is 200 degrees C. So it looks like I have this as with some writing on it, so let me erase what I have. The temperature of the copper is 200 degrees C. And then I have 150 grams of water. That's at a temperature of 20 degrees C. So is there a phase change? Not very likely. The water is well below the boiling point. Is it an isolated system? Yes, it says it's a calorimeter. So what that means is that the heat lost by the copper is going to be the heat gained by the water, and the amount of heat that's lost or gained is just going to be MC delta T because there's no phase change. So how much heat is lost by the copper? Well, it's going to be the mass of the copper times the specific heat of the copper, which is given in the problem, times the temperature change. So mass of the copper times the specific heat of the copper. So I've got M, I've got C. I know the initial temperature, I don't know the final temperature. All right, on the other side, that's the heat gained by the water. It's going to be the mass of the water, which I know. Specific heat of the water, which I know. I know the initial temperature of the water. Now, if you look at this, you see I wrote my delta T. On this side, I wrote T initial minus T final. On the other side, I wrote T final minus T initial. Why did I do that way? Well, because I wanted to get a positive number. I know the water is going to heat up, so final is going to be bigger than initial. I know the copper is going to cool down, so initial is going to be bigger than final. So because I want to get a positive number on both sides, I have to switch the order in which T initial and T final are. So if I put in, I know everything except T final. So let's put in my numbers. I've got 0.050 kilograms of copper. The specific heat of copper is 385 joules per kilogram C. Put in my initial C, temperature of 200 C. On the right side, I put 0.150 kilograms of water. 4186 joules per kilogram degree C is the specific heat. Then I've got TF minus 20. So here I've got an equation. It's a complicated equation, but it's only got one unknown in it. It's got TF. So let's first do some multiplication through to get the problem simplified a bit. So if I do my number, so I can do 0.05 times 385 times 200, that'll give me 3,850. Then 0.05 times 385 times TF will give me minus 19.25 TF. So that's what I get on the left side. On the right side, if I multiply everything together, I'm going to get 627.9 TF minus 12,558 joules. Okay, so now what am I going to do to solve this? Well, I'll take the two terms with TF over to the same side as each other, and the two terms with the energy in joules over to the other side. So I'm going to add the 19.25 to the 627.9. I get 647.15 TF is 16,408 joules. So TF is just going to be 16,408 over 647.15, or 25.35 or 25.4 degrees C. This is a very standard type of problem for this chapter. Make sure that you're able to do it. Okay, what about if we do have a phase change? So let's say I'm going to take 250 grams of steam at 150 degrees C, and I'm going to turn it into ice at minus 50 degrees C. So then I'm going to have to take the steam, cool it down, condense it into water, cool the water down, freeze the water into ice, and then cool the ice down. So I'm going to have a picture that's like the one we walked through just before, and now I'm going to be going from right to left instead of from left to right. So I've got 250 grams of steam. That's going to be 250 grams of water, and it's going to be 250 grams of ice. Okay, because that just depends, the mass just depends on how many molecules we have of H2O, so it's going to be the same. So that 250 grams is going to be my M. And then I'm just going to walk myself down through the steps using the expressions for the temperature change, either MC delta T or L times M, depending on what's going on. So first step is to cool the steam down from 150 to 100, which is where it's going to condense. Then I'm going to condense the steam into water. Then I'm going to cool that water from 100 down to 0. Then I'm going to freeze the water at 0. And then I'm going to cool the ice down. So for each step, I'm going to have a heat. So the heat for changing the temperature of the steam from 150 to 100, it's just going to be MC times the delta T. So it's going to be M, 250 grams, 0.250 kilograms. And now I need to put in the specific heat for steam, which is different to the specific heat for water, and it's different to the specific heat for ice. So I need to put in 1996. And then the temperature change is the final temperature, 100, minus the initial temperature, 150. So I'm going to get a negative energy in joules. What does that negative energy mean? It means that that heat is released. So if the heat is absorbed, it's positive. If it's released, it's negative. All right, so now I'm going to condense the steam to water. So while it's condensing, the temperature doesn't change, and the heat that I have is just M times the latent heat of vaporization. So again, I go up into my givens, take the latent heat of vaporization, multiply it by 0.250 kilograms, and while it's condensing, it's releasing the heat. So again, it's going to be a negative number. All right, so now I've finished the pink phase. Now I'm going to do the green phase where I have MC delta T again. And the C that I'm going to use in this case is going to be the specific heat for water, 4186. And the temperature change is going to be from 100 initially to 0 finally. So I'm going to do 0 minus 100. And again, I'll get a negative energy. And you'll notice that all these numbers are quite big. That's because water has a very high specific heat and also a very high latent heat. All right, so finally I'm going to freeze that water into ice. So while I'm freezing it, I'm going to use M times L is going to be my heat. And again, it's going to be negative because it's going to release the heat. And the L that I use is the latent heat of fusion because I'm fusing the water molecules into ice. And finally, I'm going to cool the ice down to minus 50. So I'm going to do MC delta T. And now the C that I'm going to use is going to be the specific heat for ice, 2090. And I'm going to start at 0 and end up at minus 50. So T final is going to be negative 50. T initial is going to be 0. And again, I'm going to get a negative heat. So as I'm going from right to left, all my heats are going to be negative. So if I want to find the total amount of heat that's released, I'm going to add up all those numbers. I get a very large number, which is about 800,000 joules of heat that's released. And again, you should be able to do parts of this. You know, if I asked you if you started with, I don't know, melting ice and you went up to steam, you should be able to do parts of these kind of calculations. All right, so I want you to do two problems then to do the two different calculations. So first problem is taking some aluminum at 550 degrees C and putting it into a calorimeter with water at 20 degrees C. And the second one is to take 2 kilograms of water that's at minus 40 degrees C, so it'll be in the ice stage, up to 150 degrees C, which will take it into the steam phase. So you're going to take the example that I just did, but you're going to go the opposite direction.